Have you ever stopped and wondered how it's even possible to get super fast internet in the absolute middle of nowhere? Well, today, we're going to break down the incredible technology behind Starlink, the system that's literally beaming internet from space to some of the most remote places on Earth. Okay, so picture this. You're running a really high-tech shrimp farm in a beautiful but totally isolated part of Malaysia. To get the best results and keep everything healthy, you need to be watching data constantly. Water quality, oxygen levels, the whole shebang. But you've got a huge problem. There's no cell service, no internet cables. You're completely cut off. So, what's the fix? Well, it's this thing. A satellite dish that's about the size of an extra-large pizza box. It claims to give you high-speed internet just by pointing it at the sky. But wait a second. How can a flat, stationary box connect to a satellite that's hundreds of miles up and moving at like unbelievable speeds? Let's get into it. All right, so to really get Starlink, you first have to understand that this is a totally different kind of satellite network. It's not just about flinging satellites into space, it's all about where you put them, and that changes everything.
The whole system really just comes down to three main parts. First, you've got your dish, the user terminal. Then, up in space, you have this massive constellation of thousands of satellites just zipping around. And finally, back on Earth, there are ground stations, or gateways, and these are the things that are physically plugged into the internet. It's a chain that connects you to space and then back down to the web.
Let's go back to our shrimp farmer. Say they want to check a live video feed of one of their water tanks. Their dish sends a request straight up to the nearest satellite. That satellite immediately bounces the request down to a ground station. The ground station pulls the video data from the internet, sends it right back up to the satellite, which then beams it down to the dish. And this whole round trip, it happens in just a blink of an eye.
Now, the real secret sauce here is the orbit. Old-school TV satellites, they're way out there in geostationary orbit, over 22,000 miles away. The signal has to travel so far that you get this awful half-second delay, or latency. That's why you can't really do video calls or gaming on it. But Starlink satellites, they're in low Earth orbit, something like 60 or 70 times closer. That slashes the travel time and gets you a latency of just 20 milliseconds. That's fast enough for literally anything you want to do online.
But being in that low orbit creates a whole new challenge. To keep from just falling back to Earth, these satellites have to move fast. We are talking 17,000 miles per hour. I mean, just to put that into perspective, a passenger jet flies at about 500 miles per hour. These satellites are circling the entire globe every 90 minutes. It's just wild.
And this isn't some design choice, it's just a fundamental law of physics. The closer you are, the faster you have to go to stay in orbit. So for our farmer on the ground, a satellite is only directly overhead for a few minutes before another one has to take over. This creates a massive technical headache. How in the world does a stationary dish track a tiny target moving at 17,000 miles per hour?
Okay, let's talk about the dish itself, because this is where the real magic happens. The solution to tracking those speeding satellites isn't mechanical. There are no motors inside moving the dish around. Nope, the magic is all electronic. See, inside that flat box is something called a phased array antenna. It's not one big antenna, it's actually a grid of 1,280 tiny little antennas, all working together perfectly. This is basically military-grade tech that's been adapted for you and me. And it's what lets a totally still object aim a beam of data with insane precision. So here's the clever part. A single one of those tiny antennas sends out a really weak signal, right? It wouldn't go anywhere on its own. But when all 1,280 of them send out their signals at the exact same moment, their waves combine. Where the peaks of all those waves line up, they build on each other. It's called constructive interference and create one single powerful focused beam. A beam that's about 3,500 times stronger than what a single antenna could do.
Okay, but how does it steer? This is brilliant. By electronically adding a tiny microscopic delay, a phase shift, to the signal as it goes across the array, you can actually change the angle of the combined beam. Think about it like waves hitting a beach. If you could slow down one side of the wave just a little, the whole wave would turn and hit the shore at a new angle. The dish does this electronically, allowing it to steer its beam across the sky in microseconds, jumping from one satellite to the next without you ever noticing.
So, let's put this all together now. We're heading back to that shrimp farm in Malaysia, and we're going to follow one single piece of data on its incredible journey from a water sensor up to space to the internet and all the way back. All right, here we go. A sensor in the tank detects low oxygen. That data hits the dish. In just 2 milliseconds, the phased array fires a beam up to a satellite. Now, because this farm is so remote, that satellite might not be able to see a ground station. No problem. It uses frickin' lasers to shoot the data packet to another satellite over the ocean that can see one. That second satellite then beams the data down to a gateway, which shoots it onto the internet. The entire round trip, for an alert to be sent and a command to come back, it can happen in as little as 30 milliseconds. Incredible.
So the really crucial point here is that this technology goes way beyond just remote farms. The power to get high-speed internet to literally anything that moves or is just far away from everything is a total game changer. It's what allows airlines to offer Wi-Fi that actually works, what keeps cruise ships connected in the middle of the ocean, and what lets emergency responders set up communication hubs in disaster zones where everything else is down.
But, as amazing as this all is, it's really important to understand what Starlink is and what it isn't. It's a very specific tool for a very specific job.
Starlink is not here to replace the fiber optic cables that light up our cities, and the reason comes down to basic physics. Starlink uses radio waves, but fiber uses light, and light has a frequency that is thousands of times higher, which means it can carry thousands of times more data. A single strand of fiber has way more capacity than an entire Starlink satellite.
On top of that, each satellite projects these focused beams onto the ground, covering a circle about 15 miles wide. And everyone inside that circle has to share that satellite's bandwidth. You can only cram so many people in there before speeds just grind to a halt. It's a system that's built for places with very few people, not for the density of a major city.
But let's bring it all the way back to where we started. For that shrimp farmer in rural Malaysia, for a scientist in Antarctica, or for a ship in the middle of the Pacific Ocean, Starlink isn't trying to compete with fiber. It's competing with, with nothing. It's the difference between being connected and being completely isolated. For millions of people, it isn't just an option. It is the only option. It makes the impossible possible.
And that really leaves us with one last massive question. For the first time in all of human history, we have the tech to bring a high-speed connection to pretty much every single square inch of this planet. So what happens then? What happens when the next brilliant idea can come from literally anywhere? What new science, what new art, what new businesses get created when every single mind on Earth is finally, truly online?